for responding. So let's start our lecture. I think you might have remembered what we discussed last week. We started our third chapter, random variables and probability distributions, right? So far you have studied probability concepts and descriptive statistics. Using the knowledge of both chapters, we will learn about random variables and probability distributions, right? Okay, I think we define what a random variable is and how to get an induced sample space from a sample space for an experiment. Anyway, I will do that part again. Yes, we did these sections. Yes, we discussed this example as well, right? We will start from this example again, okay? If you consider this example, tossing two coins, you know we will get this sample space if we toss a coin, right? Now see this diagram. Can you understand this diagram? Can you understand this diagram? Actually, on your left side, you have the original sample space for the experiment, that is tossing two coins. If you toss two coins, there are four possible outcomes. That means we can have four outcomes: HH, HT, TH, or TT. So that is the original sample space for the experiment. Now we have mapped those elements into these values 0, 1, and 2. Now, what are those values? What are those 0, 1, 2 values? Actually, in this experiment, as you can see here, we have defined a random variable capital X, okay, be the number of times that head occurs. So for this experiment, we define a new random variable capital X, that is the number of times that head occurs. Now, according to the random variable X, we are going to find an induced sample space for the same sample space or for the same experiment, right? So far, you know, this is the original sample space. Now, if you consider this single element, that is HH, there are two heads. Therefore, the value of the random variable is 2 for the first element. For the second element, value of the random variable is what? What is the value of the random variable for this case? There is only one head, no? One head, no? Therefore, the random variable is 1 because we define the variable as the number of times that head occurs, no? Okay? So the TH, it has the value of 1 again. Then for TT, there's no any head. Therefore, the value of the random variable is going to be number 0. Okay. Likewise, we have to find all the values for the random variable according to the original sample space. Okay. So here, these are the values that the random variable X can take: 0, 1, and 2. Okay. Right. Now look at the diagram again. Actually, we discussed these things last week, but it's better to start from this section. That's why I'm explaining these things again. Anyway, now see this diagram. Can you understand what we have done here? We have mapped all the elements in the original sample space to these values 0, 1, 2, which means this 0, 1, 2 set is called induced sample space or range of the random variable X, or those are the values that the random variable X can take. So we call this as the sample space And this 0, 1, 2 set is called as induced sample space. Okay. If you can remember, we define the random variable x as a real valued function. It always takes only real values. Okay, like 0, 1, 2. Over the sample space, we define those random, we define that random variable over the sample space. Or simply we can say that random variable should represent all the elements in the sample space, right? That is how we define a random variable usually. Now, classification of random variables. As we discussed in first chapter, there are two types of variables now. It can be either discrete one or continuous variable. Can you remember that? There are basically two types of data or variables. One is qualitative and quantitative, right? Qualitative can be categorized into two parts, nominal and ordinal, while quantitative can be categorized again into two parts, discrete and continuous. Here, we have mentioned about discrete and continuous data only. Why? Why is that? Why is that? So here we define the random variable according to quantitative data. Those data should be quantitative. If they are qualitative, we are not going to find any probability distribution. No, we are not going to define a random variable. Let's do that part later. For now, remember, we are going to define a random variable and we are going to find the probability function or the probability function. I will teach you those things later for a quantitative random variable. Okay, that's why we classify our random variables into two parts, like discrete random variable and continuous random variable. I hope you know the difference between discrete and continuous, right? If it is a discrete random variable, then how can we identify? It can assume only a finite or countably infinite number of distinct values. Anyway, what you need to remember is if it is a discrete random variable, it can be counted. It's a countable one. Okay. Now, again, it has a random variable that can take any value in a given interval is called continuous random variable. So if it is a continuous random variable, which means it takes any value in a given range or interval. Okay, so here we discuss only quantitative variables, discrete and continuous. Okay, these are the examples, these examples already. Height of a person, amount of rainfall, lifetime of a battery can be considered as continuous data, while number of chairs in a class, number of students in a class, likewise, there are so many examples under discrete random variable. Okay. First, we are going to discuss about discrete random variable. We will discuss about continuous random variables later. Okay. Now, tell me, we discussed this example. In this example, if you take this random variable x, tell me whether it is a continuous one or discrete one. Capital X, here it has discrete values. No, it has distinct values 0, 1, 2. So it's a discrete random variable, right? There are no any values between these values 0 or 1 or 1 or 2. Understand? Therefore, this is a discrete random variable. That means we have discussed an example with discrete random variable. Okay. Right. So far, do you have any questions regarding random variables and probability? Random variables or induced sample, how to get induced sample space for an experiment? Do you have any questions? Actually, last week also we discussed these things, right? So if you have any question, please ask me. Otherwise, we can start the next topic, probability mass function. Okay, before coming to the probability mass function, I would like to uh, review this small paragraph. Usually, it is possible to describe how the probability is associated with the induced sample space. Okay, if you can remember, last week also we discussed this, how to get these probabilities. Okay, you know the probability of getting HH is half, half times half, that is 1 over 4. No? Probability of getting HT is what? Half times half, again 1 over 4. Likewise, we have equal probabilities for this sample elements in the sample space. Okay, so these are the probabilities of the sample elements in the original sample space. Right, now look at the right hand side. Right hand side, previously we had 4 sample elements, no, but on right hand side in the induced sample space we have only 3 values. That means that random variable x can take only 3 values, 0, 1 or 2, right? Now what is the probability of getting 0 in that experiment? What is the probability of getting 0? That is 1 over 4. Why? 0 is mapped with the element tt. So the probability of getting tt is half now, which means probability of getting 0 is not half, 1 over 4 no. The probability of getting 0 is what? 1 over 4. If you consider this number 2, the value 2, probability of getting number 2 is 1 over 4. Why? Because 2 is mapped to the element HH. Now, you may have a question. Now we toss 2 coins, right? We toss 2 coins. So, if we toss 2 coins, how can we get these values? You may have a question. No? If we toss 2 coins, we may get only these sample elements, no? HH, HT, TH, TT. But here we have converted our sample space into induced sample space, right? According to the random variable we defined. Understand? The random variable in this experiment is what? X be the number of times that head occurs. That means X is a discrete random variable. Clear? Now the values of the random variables were 0, 1 and 2. No? Now we are going to find the probabilities of those values of the random variable in this. Right? Now we found the probability of getting 0 as 1 over 4 and probability of getting 2 as 1 over 4. Now tell me, what is the probability of getting 1? Here, I have given you the answer. That should be half. Why it is half? Can you tell me? Because you can see that 1 is mapped with these 2 sample elements, HT and TH. Because in HT sample element, there's only 1 head. Also, in the sample element TH, there's only 1 head. Which means probability of getting 1 is not 1 over 4. That should be 1 over 4 plus 1 over 4. 2 elements are mapped. Therefore, 1 over . diagram to 1 for any experiment, right? The total probability is always equal to 1. If you add these TT, what would you get is number 1. Half plus, 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4 gives 1. That is the total probability for this experiment. Okay. Now come to the right hand side. Now calculate or the find the addition of these. Again, you can see that 1 over 4 plus half plus 1 over 4 is going to be 1. That means total probability is going equal to, that should be equal to 1. And
Recording stopped. In progress.
my internet connection is not stable. I'm at the faculty now. Anyway, I am trying to get connected to you. Give me a second, right? My screen now?
Yes, ma'am.
Right, thank you.
Recording in progress.
We were discussing about, the random variables and induced sample space, and how to get the total probability for a induced sample space, right? Okay, now go through this small paragraph. Can you understand this? Usually it is possible to describe how the probabilities associated with the induced sample space are distributed within its subsets with a mathematical function. Such a function is called a probability distribution of the random variable. Here I have introduced you a new term, that is probability distribution. Can you understand the definition of that? This is not the proper definition of a probability distribution, right? So I just gave this small paragraph you to identify or get an idea about a probability distribution. This is not the proper definition. Okay. Anyway, probability distribution is it's a mathematical function, right? Due to the power cut, I think this is happening. Let me share my screen. You all can see my screen. Right. Okay, we were discussing about this probability distribution. Okay, now see this diagram again. Now here what we have done is using the original sample space, we have converted it into an induced sample space, okay, or a range of the random variable x, the random variable we defined here, okay. Now we are going to introduce you a function of this random variable x. Now I told you we always take capital letters for random variables, right? Capital letters. We use capital X, capital Y. But here I have written function of simple x. Because this simple x represents the values of the particular random variable x. The values of the random variable, right? That's why here I'm using simple x instead of capital X, okay? Now we are going to find a function, right, of the particular random variable x, right? Now this function fx gives probabilities, right? Probabilities of each and every value of the random variable. Understand? It's a mathematical function. So this is called probability distribution. Probability distribution. Using this probability distribution function, we can find these probabilities, right? We can find these probabilities of the random variable. Now you know there are two types of random variables, discrete and continuous, which means there are two types of probability distributions, like discrete and continuous. Understand? So there are two types of probability distributions depending on the type of the variable. Let's see what are those probability distributions. One is probability mass function, other one is probability density function. So first we discuss about probability mass function, PMF. Okay. Now probability mass function of a discrete random variable x is a function that gives the probabilities of every value of x, the random variable, and is denoted by this. Okay, I think this should be yes, this is simple x because every value of capital X, no, we have to use simple x for that, right? This is correct, okay? Which means probability mass function of a discrete random variable x is what? Is a function which gives the probabilities of every value of the random variable x. Understand? And it is denoted by px x, or we can write just px, or we can write px equals simple x like this. So this is called probability mass function. Now probability mass function means it's a probability distribution of a discrete random variable, right? Discrete. Here, discrete random variable x. Is that clear? So this probability mass function represents probabilities of every value of the random variable, the particular random variable. Understand? So let's see how to find this probability mass function for an experiment. Okay. Now consider this example. Now consider rolling a fair die. Okay. Now we roll a fair die. How many sample elements are there, or what is the sample space for this case? If we roll a fair die, we can have 6 possible outcomes. Can be either 1, 2, 3, 4, 5, or 6, because die has 6 sides. So this is the original sample space, right? Sample space of this experiment, rolling a fair die. Okay, and right hand side you have their associated probabilities, which means probability of getting 1, probability of getting 2, probability of getting 3. Okay, so this P means probability. Okay, probability. Now we are going to find a probability mass function for this experiment, probability mass function, which means if we let's say we have found the probability mass function for this experiment, right? So after finding the probability mass function, what we have to do is we have to substitute the value of the random variable. Value of the random variable. It means the value of the random variable is, let's say, that is 1, which means if we substitute 1 in the function, it should give the probability 1 over 6. If we substitute x equals 2, again it should give 1 over 6 because it has equal probabilities. Understand? So look at this table. The probability distribution can be represented as follows. Actually, there are two ways to represent their probability distribution. We can use either a mathematical function, or we can use just a table to represent the probability distribution. Understand? So in this example, capital X is what? It denotes the number of phasing up. The number, not number of, the number phasing up. If we roll a fair die, X is the number phasing up. Okay. Now X has 6 values. It can be either 1, 2, 3, 4, 5, or 6. Okay, so probability mass function means it's a function which gives probabilities of each and every value of the random variable. But in this case, right, we can use either that mathematical function or just a table to represent their probability distribution. I mean, to represent the probability distribution of the random variable x. Okay, first I will show you the table. So usually we create this table like this. First, we write value of the random variable 1, 2, 3, 4, 5, 6. Okay. Then we have to put their probabilities. I told you probability mass function can be written as either capital P x of simple x, or capital P capital X equals simple x, or P capital X. Right? These three ways are these three ways can be used. Understand? But here, instead of finding a mathematical function, we use a table to represent the probability distribution of the random variable x like this. Okay. Now, probability function that is x equals single x, 1 over 6, 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 1 over 6. That means it has equal probabilities. Okay. So if you are asked to find the probability distribution of the random variable x, if you have this kind of experiment, you can give this table. That is correct. Okay. There's another method to represent their probability distribution. Okay. That is giving a mathematical function. Okay. Here in this slide, equal signs are not shown. Let me correct it. Give me a second. Maybe I think when I share my, send my PowerPoint presentation to this iPad, equations has been changed. Give me a second, I will correct them. Okay, sorry for that. Lecture note, I will correct these changes. Okay, for now I'm writing on this slide in order to understand the equations. When I upload the lecture note, I will correct. Okay, the settings has been changed. I think that's the reason for that.
Recording stopped.
Okay, so this should be okay. Usually we write the probability mass function like this. You know, this 1 over 6 is the equal probability of this random variable. That means for any value of the random variable x, right, the probability is equal, that is 1 over 6. Therefore, the function, the mathematical function we use is 1 over 6 to represent their probabilities, or to represent the probability distribution of the random variable. But when you write that function, you have to write the domain as well. That means the value of the random variable. So x can be either 1, 2, up to 6. But we have to define another thing. What is that? So when the random variable x takes these values 1, 2, 3, 4, 5, 6, the function becomes 1 over 6. But what happens when the function takes sorry, any other value? What should be the function then? When the random variable x takes any other value, okay, other than 1, 2, 3, 4, 5, 6, what is the function? What should be the function? It should be 0. The probability of being, 0 or 7, 8, 9, 10, those should be 0. Can you understand that? I think okay, better to discuss this example again, right? Now, here we roll a fair dynamo. Now we define the random variable x as what? Number facing up, right? Now, if let's say you're asked to find the sample space for this experiment. What is the sample space? That should be 1, 2, 3, 4, 5, 6. And let's say you're asked some questions regarding the associated probabilities, okay? Which means you have to find these probabilities, the probability of getting 1, 2, 3, 4, 5, and 6. Okay, that is really easy. Let's say we want to find a mathematical function to represent these probabilities. Okay, to represent these probabilities. To do that, we use a mathematical function, probability mass function. Okay, using a probability mass function, we can represent these probabilities like this. Okay, probability of the random variable x. Now you can see that it has equal probabilities now. So we can write it as 1 over 6. But that probability is 1 over 6 if the random variable takes the values 1, 2, 3, 4, 5, 6. Otherwise, the probability is 0, which means, let's say, number 0. What is the probability of getting 0 here? What is the probability of getting 0 if we roll a fair die? Probability is 0 because we cannot get number 0 now. The die usually has 6 sides from 1 to 6. The sides are numbered from 1 to 6 now. Therefore, there's no any probability of getting number 0. So if you ask to find probability of getting number 7, that is again 0. Probability of getting number 25, if you toss if you roll a fair die, what is the probability of getting number 5? 25. That is also 0. That means this 1 over 6 is the probability when the random variable takes the value from 1 to 6. Understand? But if it takes any other value, the probability value is going to be 0. Therefore, when we write the probability mass function, okay, probability mass function, we write 1 over 6, then it's equal 0, so not 0, 1 to 6. And otherwise, the probability is 0. Understand? This is the usual way to write the probability mass function of a particular random variable x. Okay? The probability is going to be 1 over 6 if the random variable takes value 1 to 6. Otherwise, the probability is 0. Okay, so this is one way of representing probabilities, or you can use a frequency table, like not frequency, you can use probability distribution table like this. Okay, you can have a column with the values of the random variable and another column with their associated probabilities like this. Okay, give me a second.
Recording in progress.
හැබැයි ඔබට සජිත් එකක් පලාස් දෙකක් ඉන්න ඕන ඔබ ඉන්න. හැබැයි අපි කියනවා නෑ ඉන්න එපා වැඩ කරන්න කියලා. එච්චරයි වෙනස. මොකද සජිත් කියනවා ආරම්භ දෙන්නවා නෑ කියන කියවීම හින්දා. දැන් මේක තාර්කිකයි. මේකේ ලොජික් එකක් තියෙනවා. පැහැදිලි කිරීම මට කියන්න තියෙන්නේ එච්චරයි. ඒ හින්දා අරගලය තුල ඇති වෙන මේ කුණාටුකාරී සැඩ පාරවල් වගේ මේ තියෙන අවස්ථාවත් ඒ කියන්නේ ඔබ කලබල වෙන්න එපා. මෙච්චර දුර ආවේ එහෙම තමයි.
I forgot to record the lecture. No one told me why. Anyway, I have to discuss these things again with you because today there were so many problems. No? Okay. I hope you understood how to give a probability distribution for a discrete random variable. Okay, let's do another example. Okay, before going to the next example, I think we have to discuss this thing. Can you give me a 2 minute or few minutes to complete this? The slide. There are some changes need to be corrected. Therefore, give me some time. I will correct them.
Recording stopped.
මොටිවේෂන් අප්පච්චි දුව උදේම කටයුතු කරන්නේ ඔබේ ඉල්ලා සිටිනවා ඉදිරි දින 6 අපි ඕම කල්පනා
Okay.
Recording in progress.
Right. Consider this example again. We discussed this example. Now see these slides. These slides are correct, right? Okay. So can you see the probability mass function of the random variable x? So this is how we usually write the mathematical function, which is called probability mass function, because we define this mathematical function to represent the probabilities for a discrete random variable. So we call this as a probability mass function. Okay, since the random variable x is discrete, as you can see here. Okay, so when the random variable x takes these values from 1 to 6, the probability is 1/6. Otherwise, the probability is 0. But in this table, we have not included those values because when you create a probability distribution table, you have to put only the values of the random variable x. Other values like 0, 7, 8, 9, 10, 20, 50, we will not write those values in the table. You have to write only the values of the random variable x can take. Okay, but when you write a function, I know you have studied these things in functions in fundamentals of mathematics. You have to write the domain, right? So domain of the function x is what? It's a real number, no? Therefore, when you write the probability mass function like this, you have to consider other values as well, not only the values that the random variable can take. You have to define the function for other values as well. Okay, you have to keep that in your memory. Okay, now see this. Note that, right, if you add all the probabilities of the random variable x, that is equal to 1. No? Here you can see that 1/6 times 6, which gives 1. The total probability is always equal to 1. Therefore, we can write, it's an identity actually. The probability of the sample space is always equal to 1. I have told you this several times. The total probability is always equal to 1. Therefore, it's a condition. Okay, in order to identify a probability mass function, we can consider this condition. Probability of the sample space is equal to 1. Okay? And there is another condition, that is all the probabilities must be greater than or equal to 0 and less than or equal to 1, because you already know that probabilities are values from 0 to 1. Any probability cannot exceed number 1. The maximum one is 1. Therefore, it is any value in between 0 and 1. Therefore, the probability of x, or the mathematical, the probability of the random variable x is always greater than or equal to 0, because it can be equal to 0. And it can be, it is less than or equal to 1, because it can be equal to 1, right? So for any discrete random variable, the total probability is always equal to 1, and all the probabilities are, all the probabilities fall into this range 0 to 1. Understand? Okay, so using these conditions, we can identify a probability mass function of x. There are three conditions as we discussed now. The probabilities should be greater than or equal to 0, less than or equal to 1, and total probability is always equal to 1. Okay, so if these three conditions are satisfied by any function of a discrete random variable, we call or we say that function is a probability mass function of x. Understand? In general, any function that satisfies the following conditions is regarded as a probability mass function of x. You need to check these three conditions or these three properties. If all three are satisfied by the function, then it's a probability mass function of a discrete random variable x. Is that clear, guys? Now look at the second example, right? Let x be a random variable with probability mass function px equals simple x given by, here you have a table given by this table, but it mentions the probability mass function. It's okay if you are asked to find a probability mass function, you can just give a probability mass you can just give a function or this probability distribution table. It's okay. I told you there are two ways of representing probability mass function: writing a mathematical function or creating a table. Okay, so here you have a table with probabilities. Okay, now using this probability, you have to answer some questions. First one is you have to find the value of k because k is unknown. And after finding the value of k, you have to find each of the given probabilities. Probability of x less than or equal to 6, probability 3 less than x less than or equal to 6, and probability 3 less than x given that x less than or equal to 6. Okay, first we have to find the value of k. So how we are going to find this value? Now you have a probability distribution table or probability mass function of the random variable x. Here in this example, it is not mentioned about the random variable, whether it is a continuous one or discrete one, because the reason is it is mentioned that the random variable x with probability mass function. Using this term probability mass function, you have to understand here we have a discrete random variable with, because we have probability mass function. By looking at the table also, you can determine about the random variable x. Here we have a discrete one because it has distinct values. No? Understand? Which means we have a probability mass function of a discrete random variable x. Now the first question is to find the value of k. Now tell me how we are going to find this k. How can we find that value? Now there are three conditions need to satisfy, right? So first one need to be satisfied, second one and the last one. But using first one and second one, actually it's really difficult to find the value of k. Not difficult, impossible. Okay, there you will have so many inequalities. Therefore, we are going to use the third condition, that is total probability is always equal to 1. The total probability is equal to 1. So using that condition, you can easily find the value of k like this. What you need to do is you have to add all the probabilities given in the table and equate the total probability to 1. So you will have a simple equation like this. K plus 2k plus 2k plus 3k plus k square plus 2k square plus 7k square plus k equals 1 because we know the total probability is equal to 1. Now, using this equation, you can find the value of k. 9k plus 10k squared equals 1. So it's a quadratic equation. 10 times k squared plus 9k minus 1. So you can have factors like this, 10k minus 1 and k plus 1. I'm not going to teach you how to factorize these quadratic equation, okay? You know, I hope you have that knowledge now. So there may be two roots for this function or the equation, that is k equals 1 over 10 or k equals minus 1. Now tell me which value is going to be picked as the value of k, 1 over 10 or minus 1. Which value that you are going to take, minus 1 or 1 over 10? Which value, 1 over 10 or minus 1? To pick the correct value, you have to consider other conditions as well. Why? Because we have obtained two values now. One is negative, one is positive. If you substitute negative value in these probabilities, right? So the probability will be minus values. But you know, probabilities never become minus values. They are always positive, no? Positive value from 0 to 1. Therefore, we have to accept only the value 1 over 10, not minus 1. Okay, we are not going to take this minus 1. We choose 1 over 10 as the value of the k. Understand? So this is the way, or this is the procedure to find the value of k in the probability mass function, given probability mass function. Okay, right. After finding the value of k, you can again create the probability distribution table with the value of k, right? It's better to draw that table again with the value of k, right? Okay, now you have some questions to be answered. Second one, you have to find probability x less than or equal to 6. Okay, it's really important in discrete random variable or probability mass functions. Okay, it's really important to consider these inequalities and equal signs. So this is discrete one, discrete random variable. Therefore, you have to consider this equal sign also. Probability that x less than or equal to 6, which means any value of the random variable x, which is less than or equal to 6. So it can be either 0, 1, 2, 3, 4, 5, and 6, because it is equal to 6. To find that probability, you have to add all the probabilities of x which are less than or equal to 6. Like x equals 0 probability, probability of x equals 1, x equals 2, 3, 4, 5, and 6. Okay. Finally, you will have k plus 2k plus 2k plus 3k plus k square plus 2k squared. And after substituting the value of k, you will end up with 83 upon 100. 83 upon 100. Understand how to find this value of k? That is 1 over 10. And then after substituting that value of k in the probability mass function, you have to find probability when x less than or equal to 6 in this way. Understand? Okay. Now consider that part again. Probability that x less than or equal to 6, which means we have to add all the probabilities of x which are less than or equal to 6. No, this probability, this. It excludes this x equals 7. Understand? Except the probability of x equals 7, you have to add all the other probabilities to find the required probability. Which means there's another method to find that probability, because only the excluded item is 7. No, which means you know already the total probability is always equal to 1. If you add all the probabilities, that is equal to 1. But if you subtract probability of x equals 7 from 1, which gives probability when x less than or equal to 6. Okay, understand? Here I have given you that procedure as well, that method as well. We can find this probability easily in this way. Probability of x less than or equal to 6 is equal to 1 minus probability of x equals 7, because that is the only probability that we didn't consider in this inequality probability, right? So 1 minus p x equals 7, 1 minus 7k squared plus k. Finally, you will have 83 upon 100. Both answers should be same, right? The answer cannot be different. They should be same. Understand? So using that method also, we can find easily the required probability. Did you understand that? Yes or no? Well, this section is new for you, right? This is random variable and probability distributions. No? I know you, so far you have never learned these random variables and probability distribution. Therefore, please focus on the lecture. Okay, attention, give your attention on this. So, do you have any question regarding this? If you don't have any question, please do second part. Now you know how to find it. I have given you the answer as well. You have to find the probability 3 less than x less than or equal to 6. It should be greater than 3 but less than or equal to 6, which means you have to add greater than 3, no? 4, 5, 6. That means not 4, 5, 6 values. You have to add their associated probabilities. 3k plus k squared plus 2k squared. Understand? Here, x equals 4, probability when x equals 5, probability when x equals 6. I told you we are dealing with a discrete random variable. Therefore, we have to be careful when you write the summation, right? So you have to consider this equal sign as well. X equals 4, x equals 5, and x equals 6. But x cannot be equal to 3, right? Because x is greater than 3. No? Okay, finally you will get 3k plus k squared plus 2k squared, 3k plus 3k squared, 3 over 10 plus 3 over 100. Finally, that is equal to 33 over 100. Okay. Now see this one. It's a conditional probability. To find the answer for this question, right? You may, you need to remember the conditional probability formula. Okay, using that conditional probability formula, we are going to find this probability. Okay, now see the steps. I have given you the steps, you have to follow them. You know, if we have if we have a conditional probability of an event, given that another event, this is how we define, or this is how we expand that conditional probability role. that is 3 less than x, intersection x less than or equal to 6 divided by the conditional statement probability, that is probability of x less than or equal to 6. These are not new things, right? This is conditional probability. And you know, x should be either greater than 3 or less than or equal to 6. You need to consider the intersection. X should be greater than 3. And also, it should be less than or equal to 6. So what is the required region or the required probability? The probability should be 3 less than x less than or equal to 6. No, this one. Is that clear? Okay, we were discussing about this conditional probability. You know, if you have a conditional probability of A, given that B has happened, we can write this conditional probability using the conditional probability rule like this. B. Okay. But here we have 3 less than x, given that x is less than or equal to 6. Okay. Therefore, when we expand that, we have to write probability of 3 less than x intersection x less than or equal to 6 divided by probability of x less than or equal to 6, the conditional statement. Understand? So that is equal to 3 less than x and less than or equal to 6 and intersection. Right? Therefore, we write probability 3 less than x less than or equal to 6 divided by probability of x less than or equal to 6. And you may notice that probability that 3 less than x less than or equal to 6 is equal to probability 3 greater than x. Actually, here we have 3 less than x now, which means x is greater than 3. So x cannot be number 3. It should start from 4. So we write 4 less than or equal to x less than or equal to 6 divided by x less than or equal to 6. Okay, you know this probability already. 4 less than or equal to x less than or equal to 6 was found here, 33 upon 100. And that should be divided by probability when x less than or 6. Less than or 6 is found earlier, no? Here, 83 upon 100. 100 cancel out. Finally, you will get 33 upon 83. Understand here? See the answer. Did you understand how to find that probability? This is a conditional probability. If you have a conditional probability, first one that you have to do is expanding the conditional probability or the writing the conditional probability rule with the required probabilities. Okay. Then you can do the rest. Okay, this is a nice question. Example number 3. Try to do this. You have to do this example by yourself. Read the question, right? A game is played as follows. A die is rolled. If an even number turns up, the score of the game is regarded as 10. If the number turning up is 1, the score of the game is regarded as 5. Otherwise, the score of the game is regarded as the number facing up. Let x be the score of the game and find probability mass function for x or probability mass function of x. Try to do this example. It's really nice question. In this case, you may have to find the sample space as well as the induced sample space. And for the induced sample space, you have to find probability mass function. Or simply, you have to find the probability mass function of the random variable x. If the random variable x is the score of the game, okay, you have to identify the sample space and induced sample space separately, right? Okay, try to do that. Okay. A game is played as follows. A die is rolled. A die is rolled. Now tell me what is the sample space when we when we roll a fair die? If we roll a fair die, the sample space would be 0, 1, 2, 3, 4, 5, 6. Okay? Right. Now that is not the random variable x. X is the score of the game. A die is rolled. If an even number turns up, it says if an even number turns up, the score of the game is regarded as 10, which means when we roll a fair die, if we get an even number, we record the score of the game as 10, which means we have to map this 10 to 0, 2, 4, and 6 because they are even numbers in the sample space. If we get either number 0, 2, 4, or 6, the score of the game is regarded as 10. Okay, right. If the number turning up is 1, the score of the game is regarded as 5. If the number turning up is 5, number turning up is 1, the score of the game is regarded as 5. Okay, right. Otherwise, score of the game is regarded as the number facing up. If these two happens,
Recording stopped.
can you hear me? Hello, are you there, students?
Yes, madam.
Okay. Very sorry for the internet connection issue. Anyway, we have to finish this section today because yesterday also I couldn't conduct the lecture as it is Friday. Okay, there's a question from a student. Can we get 0 as sample space? It's not in that. Okay, I will ask. I will answer that question later. I think mistakenly I have written that 0. Yes. Sorry for that. So in this example, we are rolling a die. No, die has 6 sides from 1 to 6, not 0. 0 is not there. Thank you for reminding me. Okay, 0 is not there. Only the sample space has 6 elements. No? 1, 2, 3, 4, 5, 6, which means there are only 6 possible outcomes. Now, the sample space for the experiment is 1 to 6. Okay, no, 0 is not there, sorry for that. But the random variable x we define here is the score of the game, not the number facing up. Therefore, we need to find the induced sample space according to the score of the game, right? According to the score of the game. Now, it says if we get an even number, the score of the game is regarded as 10. So that means if we get number 2, 4, or 6, the score of the game is 10. Okay. Further, it says if we get number 1, okay,
Recording
if we
in
get
progress.
number 1, then the score of the game is regarded as 5. And otherwise, the score of the game is regarded as the number facing up. There are 2 more values now. If we get number 3, then the score of the game is regarded as number 3. And if we get number 5, the score of the game is regarded as number 5. But we don't need to write that number 5 again because 5 is already recorded. No? Therefore, we can map that 5 into this 5. We don't need to write this 5. Understand? Which means the original sample space has 6 possible outcomes, while the induced sample space has only 1, 2, 3 possible outcomes, or the values induced sample space has 3 values for the random variable x. Understand? It can be either 10, 5, or 3. Now see this diagram. Here this is not 1 over 1 and 0. This should be 10. I told you the settings has been changed when I send this PowerPoint to the, this Apple iPad. Anyway, I will upload corrected lecture note, okay? You don't have to worry about it. When I upload the lecture note, I will upload the correct one. Anyway, we have the sample space like this, and we have found the induced sample space according to the random variable x, okay? Now we are going to find associated probabilities because that is the target. In the question, we are asked to find the probability mass function for the random variable x. Okay, that's why we found the induced sample space. Now we are going to find associated probabilities. Before finding these probabilities, associated probabilities of 10, 5, and 3, better to find associated probabilities of each sample element in the sample space, original sample space. And you know, the associated probability of 1 is 1 over 6. No? The probability of getting number 1 is 1 over 6. Since the die is fair. We have a fair die now. Therefore, the probability of getting number 1 is 1 over 6. 1 over 6, 1 over 6, 1 over 6, 1 over 6, and 1 over 6. Now we have mapped these values into the values of the induced sample space. Now number 10 is mapped to 3 values now. 1 over 6 plus 1 over 6 plus 1 over 6, that is half. 3 over 6, that is half. That means probability of getting number 10 as the score of the game is half. Probability of getting number 5 as the score of the game is 1 over 6 plus 1 over 6, that is 1 over 3. That means 2 over 6, that is 1 over 3. Okay, right. The probability of getting number 3 is 1 over 6. That is 1 over 6. Okay, now there's a question from a student. How the score of the game becomes 3 when the number facing up is 3. Okay, you are asking how we map these 3 into 3, no? Okay, I will explain that again. Here, read the question carefully. It says, if we get an even number, then the score of the game is regarded as 10. It's clear. Now we have 1, 2, 3, 4, 5, 6 now. So if we get even number, 2, 4, 6, the score of the game is 10. Okay. If the number turning up is 1, the score of the game is regarded as 5. If we get number 1 in the die, which means the score of the game is number 5. Clear? Now it says, otherwise, the score of the game is regarded as the number facing up. That means if we get, now we have 2 more values now, number 3 and number 5. We can get these 2 values as well. So if we get number 3, what should be the score of the game? That is equal to, regarded as the number facing up. That is equal to 3, the same number. If we get number 5, that should be equal to 5, but we are not going to write number 5 again because we have already recorded number 5 here. Understand? So this is how we map our sample space into induced sample space. Okay, I hope now you understood how to map that. Okay, now see the next slide again. So we were discussing how to write associated probabilities. Now we have found associated probability of 10 as half, 1 over 3 and 1 over 6. Now, you know the total probability is always equal to 1 for any experiment. Better to add these probabilities to check that. 1 over 6, that is equal to 3 plus 2 plus 1, 6 over 6, 1. Which means we have found this induced sample space and their corresponding probabilities correctly. No, the total probability has been 1 now. Okay, now we have to answer the question. What was the answer, question in this problem? To find the probability mass function. Okay, now let's write the probability mass function for this experiment. Px x, or you can write Px equals simple x. How can we write? It can be either 3, 5 or 10. 3, 5 or 10. the probability is not 3 or 3, 5 or 10. We are writing the probabilities now. Sorry for that. We are not writing. Probability cannot be a value greater than 1. What are the probabilities? Probabilities are half, 1 over 3 or 1 over 6. Those are the probabilities. Half, 1 over 3 and 1 over 6. And there's another probability that is 0. Okay. The probability is half when x equals 10. Probability is 1 over 3 when x equals 5. Probability is 1 over 6 when x equals 3. Probability is 0 otherwise. Understand? Is that clear? Here we want to write probabilities, right? Not the values of the random variable. So we want to find the probability mass function now, which means a mathematical function to represent probabilities. So half, 1 over 3 and 1 over 6, 0. It becomes half when x equals 10. It becomes 1 over 3 when x equals 5. When x equals 3, the probability is 1 over 6. Otherwise, the probability is 0, which means if the random variable x takes any other value, apart from this 3, 5, and 10, the probability is going to be 0. Okay? So you can use just a table to represent the probability mass function like this. Okay, both are correct. So that is the answer for this problem. So here we have found these probabilities. Okay, I have shown how to find these probabilities. Finally, we can write the probability mass function of the random variable x as follows. Okay. This is called probability distribution or probability mass function. If you want to write a mathematical function, you can just write, I have written it earlier also, x equals x, 1 over 6, 1 over 3, half, when x equals 10, when x equals 5, when x, these are simple values, right? Because here we are considering the values of the random variable, 10, otherwise. Understand? Okay. Now we have to discuss cumulative probability distribution. I have 8 minutes more. I think I can explain that as well. Okay. It's a small part. Cumulative. You know, if you have a frequency table, you know how to find cumulative frequencies, no? How to find cumulative frequencies? Huh? Let's say we have a frequency table, XF. 1, 2, 3, 4. The frequencies are particular frequencies are 2, 4, 5, again 1. The total frequencies 12. Okay, now you have a frequency table, and let's say we want to find cumulative frequency. Cumulative frequency. How we are going to find cumulative frequency? Cumulative frequency means you have to add the frequencies. When x equals 1, the frequency is 2. Its cumulative frequency is still 2. when x equals 2, the cumulative frequency is 4, not cumulative, the frequency is 4. Corresponding frequency is 4. What is the cumulative frequency? Cumulative frequency is not 4. You have to add both 2 and 4. 2 plus 4, that is 6. The cumulative frequency when x equals 3 is not 5. 6 plus 5. All the frequencies, 2 plus 4 plus 5. And the cumulative frequency when x equals 4 is 2 plus 4 plus 5 plus 1, that is 12, or 11 plus 1, that is 12. If you have obtained cumulative frequencies correctly, that means you have to end up with the total frequency at final row, or the final cumulative frequency row. Is that clear? So this is how we find cumulative frequencies for a frequency table. But here we do not have any frequency table. Instead of a frequency table, we have a probability distribution table or probability mass function. Okay, so for that probability mass function or the probability distribution table, we are going to find cumulative probability distribution. Okay, right. Before finding the cumulative probability distribution, before that, better to answer these questions. Then you will understand how to find the cumulative probability distribution after answering these questions. Okay, see the first question. What is the probability that x is less than or equal to 3? Here 1 over 6 means what? That is the probability when x equals 3. X equals x means when x equals 3, the probability is 1 over 6. Now it asks, what is the probability that x is less than or equal to 3? Less than or equal to 3, which means you have to add 0 and this not 10, this is 3, no? When x equals 3, the probability is 1 over 6, no? This is 3. So the probability when x less than or equal to 3 is still 1 over 6. You have to add these two, 1 over 6. Now tell me, what is the probability that x is less than or equal to 5? Less than or equal to 5. You have to add this and this. 1 over 6 plus 1 over 3, that is half. This half means what? Not the probability when x equals 5. This half means probability when x less than or equal to 5. Okay. So if we want to find probability when x less than or equal to 10, the answer for the third question, probability that x is less than or equal to 10, that is probability of x when x less than or equal to 10, that is half plus 1 over 3 plus 1 over 2, that is equal to 1. So this table is called cumulative probability distribution table or probability distribution. Understand? Here, based on probability distribution, we can easily calculate probabilities for values that are less than or equal to a given value, like this. Okay? Therefore,
madam
yes.
මේක මේ ඒ විදිහට හොයන්න නැතුව නිකන් ඇඩ් කරලා වුණත් යන්න පුළුවන් නේද මෙතන?
Of
1 over
course,
6.
1 over 6 plus 1 over 3 plus 1 over 2. That is the probability when x less than or equal to 10. Total probability is 1. If you want to find this one, you can add just these two probabilities. Right? Clear?
Yes, madam.
Okay. Now, if you have done it correctly, right, the last cumulative frequency, cumulative probability should be 1. No, you know the total probability is always equal to 1. Therefore, the last cell should be number 1. Right. Now, there's a proper way to represent that cumulative probability. There's a proper way. That is, there's a proper mathematical function. Okay. So previously I have written it as probability when x equals x. No, this is correct. This is correct. This is correct for the cumulative probability. But we can use a mathematical function to represent this probability, cumulative probability. Okay, that function is going to be capital F. We always use capital F to represent cumulative probabilities. Okay, so the function capital F of x, that is equal to, this is the cumulative probability distribution of the random variable x, and that is equal to probability when x less than or equal to simple x. Understand? Is that clear? So instead of this f of x, you can just write probability of x less than or equal to simple x. Both are correct. Let's say for the same distribution, okay, you want to find f of 3. F of 3. Now, what do you mean by f of 3? Capital F means cumulative probability distribution when x equals 3. When x equals 3, right? When x equals 3. Or you can write this as f of x when x equals 3. Both are correct. Or you can write f x equals 3. Now, how to find this probability? Now, you want to find f of 3. F of 3 means what? This 1 over 6. Probability of x when x is less than or equal to 3. That is 1 over 6. Let's say you want to find f of 10. What is f of 10? Which means f when x equals 10. That is equal to probability of x less than or equal to 10. That is what? 1. Clear? Okay. Let's say you want to find f of 12. Can you find this probability? F of 12? What is that probability? Please tell me, hurry up. F of 12. Is it 0 or does it have a value?
0.
Is it 0? Others? F of 10 means what? If you are asked to find probability when x equals 12, definitely it's going to be 0. Because there's no any probability when x equals 12. But you are asked to find cumulative probability of 12. F of 12 means what? Probability when x less than or equal to 12. Less than or equal to 12, there are 3 values that are less than or equal to 12. What are those values? 3, 5 and 10. Which means you have to add all the probabilities. Half plus 1 over 6 plus half plus 1 over 3 plus 1 over 6. Or without adding those probabilities, you can just write number 1. When the value of the random variable x exceeds its maximum value is 12, it is greater than 10 now, the cumulative frequency, not frequency, cumulative probabilities going to be 1. Understand? If you are asked to find f of 50, that is also 1. If you are asked to find f of 4, now 4 is not there. 4 is not in the table, but still you can find f of 4. How? F of 4 means probability when x less than or equal to 4. Now 3 is less than 4. Therefore, you have to select probability when x equals 3, 1 over 6. Understand? Did you understand it? If you are asked to find f of 8, what is the answer? Quickly tell me. F of 8, what is the answer? F of 8. F of 8?
Half.
Half. Very good. That should be half. Understand? So this is called cumulative probability distribution. Right? So far we discussed how to find induced sample space and the associated probabilities and probability mass function of a particular random variable and cumulative probability distribution for a discrete random variable only. Okay, we will discuss about continuous random variable later. Next week we will discuss about mathematical expectation of a discrete random variable. Simply expected value of x and variance of x. That means mean and variance. So next week we will discuss how to find mean and variance when we have a probability distribution or probability mass function. Okay. I will upload this lecture note within this week. Okay. You have to refer the lecture notes before coming to the next lecture. Okay. So far, do you have any questions? Okay, if you have any question, you can just email me or WhatsApp me. I'm going to stop the lecture for today. Thank you for joining the lecture. Have a nice day.
Thank you, madam.